Okay, thank you for the introduction, and thank you everybody for being here. In this presentation, I'm going to be talking about our work, Hodor, a system designed to provide intra-process isolation for data plane libraries. This is a collaboration with Spyridoula Gravani, Ethan Johnson, John Criswell, and Michael Scott from University of Rochester, and Shen and Mike Marty from Google. In conventionalized stack design, access to devices is mediated basically by operating system kernel. It's the responsibility of OS to multiplex devices and enable sharing of resources among applications, as well as enforce fairness, security, and reliability policies among applications. These policies might, for example, prevent an application from monopolizing the device, protect applications from corrupting each other's data, and recover the state of the application after a power failure. The OS is able to provide these guarantees without needing to trust the applications, since it is protected from malicious or buggy applications through user kernel isolation. However, as devices with microsecond latencies and throughputs of millions of IOPS made their way into data centers, people started to move IO stacks out of the kernel and into user space, usually implemented as libraries. This allows for lower latency and higher throughput. It allows for rapid development cycles because it's easier to write code in user space. And specifically, it allows for specialization. Say you don't need all the features that kernel stack provides. You can roll your own, and you can basically simplify it and gain performance this way. We loosely call all of these libraries data plane libraries. It could include network libraries like DPDK, SPDK for storage, but also in-memory key value stores or non-volatile memory libraries that guarantee that you can recover after a power failure. So the problem is that if data plane libraries are simply mapped into the user space application's address space, the lack of isolation means that any guarantee that these libraries are providing is effectively void. A vulnerability, like a stray pointer in the main application, can corrupt the state that is maintained by these libraries. Or even worse, a malicious application can completely circumvent these libraries and access the device directly. And finally, because of this lack of isolation, multiplexing the underlying resources when you are using data plane libraries to access the device is basically very challenging when applications are distrusting. Okay, so now that we have established what data plane libraries are and why they are important, why they are going to become even more important in the future, and that we need isolation to share data plane libraries, I'm going to talk about our solution to provide isolation without basically negating everything that you are basically reaping from doing kernel bypass. For the rest of the talk, I will focus on our work on Hodor. First, I will describe the high-level design of Hodor. Then I will show how we achieve fast memory isolation using Intel protection keys for user space. And then we show the experimental evaluations, and finally we conclude and discuss future direction. Okay. In order to achieve isolation, we introduce protected library as a new OS abstraction. Hodor partitions application into multiple domains of executable code. Each domain is granted access to some part of the address space and denied access to some other parts of the address space. Each domain has a private stack. It can also have private heap, but also shares access to some part of address space for efficient communication with other domains. In this figure, you see the main application in a separate domain from network and storage protected libraries, which have their own domain. But the point is that any access to either of these storage or networking device has to go through the appropriate library. The interaction between the application and the libraries is like it was before, through function calls and returns, following the standard calling convention. However, in order to ensure isolation, these transitions are mediated by a trampoline that switches to the appropriate domain before handing over the execution to the library. You can think of trampolines as wrappers for the exported API of the protected library. And in our solution, they are inserted automatically by our program loader. But they can also be inserted at link time. Trampolines also need to safely switch stack, copy arguments to maintain calling convention, and also scrub registers to make sure that we are not leaking information. Okay, let's take a look at the process of using Hodor. So if you want to use Hodor, what are the steps that you have to take? To start with, our design doesn't require the main application to be modified. That's because this is the default policy. The application shares its entire memory space with protected library. So it trusts the protected library. Of course, if you're not happy with that, you can change the application in order to share only parts of it with protected libraries. The only codes that need to be ported to Hodor are the protected libraries. This is required because the protected library needs to use appropriate flags to indicate to OS memory regions that need to be shared with the application. And it also needs to indicate information on exported API so that the loader can insert appropriate trampolines at load time. In our experiment, these changes are relatively straightforward, at least for the protected libraries that we used. Two main components of our design are Hodor's loader and the modification that we added to the Linux kernel. The job of the loader is to basically parse the information that comes with the protected library, some metadata that we add, and load the library in its own domain, insert the trampolines, initialize the library. It will also communicate the address space layout with the kernel so that during the course of execution, the kernel can guarantee the integrity of basically this setting. In the next part, I'm going to be talking about how we achieve fast memory isolation to protect libraries. Starting with the Skylake SP, Intel introduced protection keys for user space, also known as memory protection keys or MPK, which enables an address space to be partitioned to 16 different domains. It introduces 4 previously unused bits in the page table structure called PKey to identify which domain a page belongs to, and the 32-bit register called PeekARu to disable access or write to each of the 16 domains indicated by this PKey. It also introduces 2 unprivileged instructions for reading and writing to the PeekARu register. This figure shows how PeekARu affects the access permission of a page. On a memory access, basically we use TLB, and the cache translation determines the legacy permission to the page. It also determines which protection domain this page belongs to using the PKey value. Then we use this PKey value to basically look up into the PeekARu register to determine PeekARu permissions for that domain. Then the final access right is going to be the intersection of legacy and PeekARu permission. As it turns out, the PeekARu feature can be directly used to provide different protection domains in Hodor. The loader basically needs to assign appropriate PKeys to pages based on which protection domain they belong to. Either they are application or the protected library, and which protected library. And the trampoline needs to grant or deny accesses appropriately using the PeekARu register when transitioning into and out of a domain. The example in this figure shows each domain with a different color next to the application and the libraries. You see the keys representing the domains that they can access with the corresponding color. For example, here the main application can only access its own domain, while protected network library can access both its own and the application's domain. Unfortunately, this design is not safe. So why not? Because the instruction that modifies PeekARu register, which is the write PeekARu instruction, is unprivileged. So we cannot guarantee that the access rights are granted only when transitioning through the trampoline. Continuing with the previous example, a malicious application can grant itself access to domain of protected network library by using the write PeekARu instruction here. Okay, in order to ensure the application can never grant itself right that has not been intended by Hodor, we have to ensure any write PeekARu instruction outside of trampoline that we craft and we insert and we guarantee that they cannot be used in malicious way are vetted. To this end, Hodor inspects all executable pages at load time or whenever during the course of execution that they become executable, looking for the byte sequence that can be used to execute write PeekARu instruction. Since it is undecidable to know in advance for x86 at least whether such a 3-byte sequence is a real instance of write PeekARu as opposed to data embedded in code or spanning legitimate instructions, we do not rely on disassembly of the executable region and mark all these occurrences as potentially malicious. In the example here, on the left, you can see an intended use of write PeekARu from libc, and on the right, an implicit instance spanning neighboring instructions. However, since the control flow can be violated to basically start in the middle of the load effective address instruction, we need to vet these instances as well. Once all of these illegal instances, once they have been identified, Hodor relies on hardware watchpoints or debug registers to vet the execution of all write PeekARu instructions outside of trampoline. A hardware watchpoint is going to be programmed basically to point to the beginning of this 3-byte sequence, and it will cause an exception if and when the sequence is used as a write PeekARu instruction. Note that data access, if you have data embedded in the code, or in the case of implicit instances, like this figure, correctly aligned execution will not cause exception. But the problem is that we have only a limited number of hardware watchpoints. We have only 4 on Intel processors. Because of this, we use the hardware watchpoint, the set of hardware watchpoint, as the cache for the set of potentially illegal sequence. So when we map a page that has this illegal sequence, we map it as non-executable. Upon the first access, the hardware watchpoints are going to be reclaimed and used to point to these instances, and from that point on, the page is going to be marked as executable, or until we need to reclaim these registers again, if we ever do. In extremely rare case that there are more than the number of watchpoint instances in a single page, we have to basically do single step through the page. So what is the cost of vetting the write PeekARUs? So there are different categories that I want to go one by one. Note that implicit instances are never really executed. I mean, unless your program is already hijacked, are never triggered. So there's no vetting cost for that. Applications that really need to use PeekARu for internal isolation, they need to use this API using the PeekSet function from libc to change the PeekARu register. And we have modified the PeekSet in libc to guarantee it cannot be exploited. So we also don't need to vet these instances. And our experiment also shows that there is no measurable overhead as long as the number of hot illegal instruction hot illegal sequence are fewer than the available number of watchpoints. To put that into perspective, we inspected RPM packages on Fedora distribution, which amounts to more than 100,000 executable and libraries. Within these binaries, we found only 123 binaries with 1 or more instances of illegal byte sequence, only 2 of which have more than 4 instances. Therefore, we don't expect the limited number of hardware watchpoints to cause any significant overhead for real applications. And for the record, none of the applications that we used for experiments had any instance. We implemented Hodor also with 2 alternative memory isolation techniques and compared it against the PeekARu approach that you can see in the paper. The first one is basically separate page table for each domain, and inside the trampoline we do a syscall. We change the CR3 register to point to the appropriate page table. And the second one is similar, but it uses extended page table, and then we use vmfunc instruction inside the trampoline to basically switch domain without calling into OS. However, the second one is only available if you are already running inside VMX. We evaluated 3 real-world applications and real data plane libraries. We evaluated the effect of Hodor on a in-memory database, on a kernel-bypass TCP/IP stack, and on Intel's data plane development kit. In the interest of time, we are not going to discuss the DPDK. Please see the paper for that result. But these images here, they show the setting for Silo and Redis. On the left, we use Silo, which is a library that can be used to write scalable in-memory databases for multi-core machines. We use this library to provide in-memory key value store and in-memory OLTP interface. Then we use YCSB and TPCC benchmark to evaluate the cost of using the in-memory database as a protected library. Similarly, we used Redis, which is another in-memory key value store, which serves a request over network, but we replaced the kernel networking with fstack, which is a kernel-bypass TCP/IP stack. In this instance, the network library is basically protected from any vulnerability that may exist in Redis. So here are the evaluation results. We measured application-specific throughput metric for both of the applications, and higher is better here. As you can see, PeekARu, which is the yellow bar, provides the lowest overhead compared to the red bar, which is the unprotected case. And for YCSB, the PeekARu approach reaches more than 2 million transitions per second per core. And across the board, it's within 90 to 98% of unprotected case. vmfunc seems to be the second best alternative. And in the paper, we detail the trade-offs between using PeekARu or using vmfunc. To conclude, we introduced protected libraries as a new OS abstraction. We also showed that we can use Intel PeekARu in a safe way to isolate protected libraries without sacrificing performance. What we didn't talk about here is how we can use Hodor to share resources and these protected libraries, which you can see the paper for that. And with that, I would be happy to take any questions.
We can take a couple of questions.
Hi. This leaves, of course, open all of the issues of unsafe programming languages and the arguments into the libraries and the pointers and all of the other stuff that can be caused to trip the library, return-oriented programming, whatever, to smash the library state.
Right. So all of these problems are going to exist in our system. The point is that what we are offering is a solution that you can lift the services that were written in the kernel to user space, and you have to take the same care that you would care if you were to write them inside the kernel. So you have to do copy in, copy out. You have to check the arguments into and out of the libraries. But the benefit is that with somewhat minor modification, you can basically use DPDK with Hodor. Yeah, it would be great if we could basically, all of us, we could switch to a programming language that doesn't have these problems.
I'm curious, how do you compare with ARIM, which essentially uses MPK but inspects the binaries, right, and just does the rewriting? And I really appreciate your contribution about these hardware breakpoints. It's very cute, but can you provide some comparison?
Okay, so ARIM is a concurrent work. If some of you don't know, it's going to be presented, I guess, in using security in a few weeks. So the approach that ARIM uses is static binary rewriting. And static binary rewriting for x86 is undecidable. You don't know this byte sequence that you see in executable region, if it is code or if it is data that is embedded here. And so again, because of the same results that I showed here, that this byte sequence rarely happens, ARIM is going to work 90% of the time or 99% of the time. But there are some cases that basically is going to break the application. Now, if you actually read the paper, I think they have basically inspected like 2,000, I guess, binaries, and they couldn't basically disassemble 200 out of these 2,000 or some number like that. See the paper for that. But yeah, basically, that's undecidable. So you can get away because it doesn't happen that frequently. But
Thank you.
Yeah, thank you.
Speaker to start setting up. I'll take maybe one more question, and then we can. Thank you.
Yeah, thank you. I appreciate also this talk too. I have another question about using the Intel PeekARu in a safe way. So have you considered, or like, how would you handle just-in-time compilation or any self-modifying code, or if that would produce any problems?
can you repeat the question again?
If you had a self-modifying code that could introduce that instruction, or a JIT compiler that can, in some ways, can imagine was a way to output that instruction, if there's a way for you to check for that.
So we didn't experiment with that, but we have thought about it. And the point is that we can support JIT compilers. Basically, we have to guarantee that if it is writable, it's not executable. And the first time that you are going to execute it, we are going to reinspect it, and then we can proceed the same way that we are proceeding here. But natural question is going to be, what's the overhead? And we didn't experiment with that. Yeah.
All right, thank you.
Thank you. Let's thank the speaker.